last time we looked at how we could appropriately interpret sine and cosine as the opposite and adjacent edges or lengths of the opposite and adjacent edges of an appropriately chosen right-angled triangle. Thinking about kind of the unit circle and stuff like that, as long as theta, the angle, was between 0 and pi over 2. And using that interpretation, we were able to extract an interesting relationship between sine and cos. Namely, if we applied Pythagoras' theorem, we got cos squared of theta plus sine squared of theta is equal to 1. So this is a really important property. Now, as I'm sure you're aware, there are lots of other trigonometric identities, so relationships between sine, cos, and all these things. There's loads of different ones of escalating complexity. So I always get the feeling when I'm talking to people about trigonometric identities, they don't like them very much. And I can understand why. They're very elaborate looking. They look kind of like scary mathematics. The way they're applied can be difficult. And yeah, I think it's just a difficult part of the curriculum. So something I do want to say, maybe to put your mind at ease a little bit, is when it comes to calculus, extremely elaborate trigonometric identities are not an integral part of it at all. In fact, what I'm going to go through now are the identities that are important and do turn up to some extent in calculus, but only to a very small degree and only in very specific instances. So, for example, the identities I'm going to go through now, I mean, really, they will turn up a little bit in your kind of first classes. They're more likely to turn up in maybe a second course in calculus, maybe something like 16B or 1B or something like that. But it's important to know them because they turn up in specific moments, and as I say, if you are completely unfamiliar with them, things can be a problem. So the first ones I want to look at are angle sum formulas. And I'm not going to justify any of these because it will take us a bit too far afield. It's not so important. It's more important that we kind of get the shape, the structure of them. So angle sum formulae. So this is asking, how do sine and cos interact with addition? So cosine of A plus B. So this turns out to be equal to something not at all obvious. This is equal to cosine of A, cosine of B minus sine of A times sine of B. Now, I don't think anyone who sees the definition of cosine looks at it and thinks, oh, that's completely clear. Cosine, remember, represents the x-coordinate on a unit circle. So this is a really kind of difficult thing to see geometrically. So as I said, this is not obvious. Not obvious at all. Turns out sine has 1, 2, which is equally not obvious. Maybe a little bit prettier, it's a bit more symmetric. But sine of A plus B turns out to be equal to, so I'll write it like this, cos of A sine of B plus cos of B sine of A. I think that's a little bit more elegant, that formula. Again, neither of them are obvious. So these are my angle sum formulae, if you want. So as I said, I'm not going to justify them. There are kind of nice justifications, but they'll take us a bit too far afield. Something I desperately want to highlight, though, is this doesn't work like the distributive property. A lot of people look at these formulas and think, oh, I'm used to seeing the distributive rule, so maybe it works, as you might guess. So what I mean by that is the following. This guy is not equal to cos of A plus cos of B. You see, if you look at this and you think, oh, I will just apply the distributive property, then you might think this is the case. But cos is my symbol for a function. It's not a number. If cos was a number, then brilliant, right? It would work, but it's not. This is a kind of a general statement about notation. You've got to be fully aware of what the notation stands for. So just, if I have a function f, right, and I have a plus b, it's incredibly tempting to write down this. Because you think, oh, but that's exactly what the distributive property is. But only if f represents a number. If f is a letter representing a function, then absolutely not. There's no reason to think this is going to hold. So this is an important point. When you're using notation, don't just be blind to what it means. Think, what do the symbols represent? Do they represent numbers? Do they represent functions? All this kind of thing. So this is a really serious mistake, right? This thinking it's cos A plus cos B. And the same thing is exactly true. The same thing is true down here. So this is absolutely not equal to sine of A plus sine of B. I've countless mistakes I've seen in exams where people just blindly write this down because they are so used to writing it for numbers with distributive property, they don't realize what they're dealing with. Okay, so angle sum formula. Good to know, basically. These guys as well give rise to a few more. So let's do a special case. So I promise you there's not going to be a huge number of these things, but I just want to show you how these give rise to a few useful identities that you should know. So special case. Well, let's have A is equal to B. So then what do you have? This would give you cos of 2A is equal to cos of 2A is equal to cos squared of A minus sine squared of A. That's a useful one to know. It's kind of called double angle formulas. And sine of 2A, well, now the A and the B are exactly the same, so it would just be 2 cos of A sine of A. So these are often called double angle formulas. Let's leave them like that. So they're kind of consequences. They are coming from the ones above. They're the more major ones. So this, of course, is cos of A plus A, and this, of course, is sine of A plus A. That's all I'm doing is applying the above formulas for this. Okay, so a couple of useful consequences of this. So actually all I'm going to talk about here is this angle sum formula. It's the only formula I think's relevant beyond the Pythagoras one to most of calculus. So useful consequences. So you can do something pretty neat with these. It's not at all obvious. So let's take the cos one for a second. So cos of 2A is equal to cos squared of A minus sine squared of A. Now this looks terribly like my Pythagoras one, doesn't it? Which is cos squared of A plus sine squared of A is equal to 1. So let's remind ourselves, so maybe I should be a bit more uniform. So let's just remind ourselves that cos squared of A plus sine squared of A is equal to 1. So this implies that, well, let's solve this for sine squared. It's 1 minus cos squared of A, yeah? So I could actually substitute that into this formula, couldn't I? So I could write this as cos squared of A minus 1 minus cos squared of A. Bit of a weird thing to do, but let's kind of run with it. So what's this equal to? This would be equal to 2. So doing the algebra carefully, it's got a minus 1. So then I could solve this for cos squared. So this would give me cos squared of A is equal to what? Is equal to 1 plus cos of 2A all divided by 2. Doesn't look too earth-shattering, but it's a useful formula in the world of calculus. And I'll tell you why it's useful. It's useful because, okay, imagine if A was like a variable here, like an x or a theta. Then this allows you to write down cos squared of theta in terms of, well, something much simpler, which is cos of 2 theta. And this, for example, this side, this is kind of a natural series of transformations away from cos of theta. Right, so you could do a horizontal compression by factor 2, then you could, I don't know, translate up by 1, and then you could compress by factor 2, right, vertically. So it's quite a useful thing to do. This is the reason this is useful, is because it gives you a relationship between kind of cos squared of theta and just cos of theta, albeit up to a few transformations. So if I've got this, we could also do the following. We could replace the cos squared with What with 1 minus sine squared? So this would imply that 1 minus, so this is just Pythagoras' theorem again, is equal to 1 plus cos 2a divided by 2. So then this would imply, let's solve this guy. The sine squared a is equal to 1 minus plus cos of 2a divided by 2. So let's do this super duper carefully. This is 2 divided by 2 minus 1 plus cos of 2a divided by 2. So I've made the denominators the same. So putting all this together, I would get 1 minus, so 2 minus 1 is 1, all divided by 2. Okay, so let's just write that conclusion again. That's the statement that sine squared of a is equal to something very, very similar to the one of 1 minus cos of 2a divided by 2. So it's a minus as opposed to a plus. So again, this is useful because it will allow you to represent the function sine squared in terms of cosine, or at least a few transformations away from cosine. So there may be a few more your professors introduce, but they won't be too crazy. And I think the two that really matter the most are the Pythagoras' one, of course, because Pythagoras gives me, well, Pythagoras is just very fundamental. It gives you a relationship between sine and cosine, very important. And then, of course, the angle sum formula and their consequences, which are just given here. So I don't really think you need any more than that, particularly for your early calculus classes. So don't be worried about having to memorize 20 different crazy trig identities. It's not what calculus is about. It's not what the focus is going to be on. What overwhelmingly matters in terms of trigonometry is the behavior as functions. So sine, cosine, tan as functions. That's what matters, not these kind of slightly out of the blue, weird algebraic identities involving them, which is kind of what you focus more on when you think about trigonometry at high school.